Alright, so today's lesson is going to be on power and safety in electrical circuits. So let's start with power. Now whenever you go and buy a light bulb, it might say 15 watts. Alright, well, what's a watt? I mean, we've talked about electrical energy in terms of joules, right? And let's say a light bulb gives out 15 joules. But then the question is, when does it give out 15 joules? If you have it continually on, does it give off 15 joules for the entire time that it's on? What if someone only turns it on for a second? Does that give off 15 joules? Right? That represents a problem. So we need power. Now, if you remember, we studied power on our energy unit, and power is the rate of transfer of energy. So it's change in energy over time. So what a 15-watt light bulb is it tells you this light bulb uses 15 joules of energy every second. So now you can tell the difference between how much joules somebody uses if they have the light bulb on for a minute, an hour, or a day. There'll be different amounts of energy, which makes sense. Okay. Now, we calculated power back in our energy unit as change in energy over time. How we're going to calculate power in an electric circuit is voltage times current. So in an electric circuit, power equals voltage times current. We can write this triangle to help us solve for whatever variable we want to solve for. And that's on your handout. Okay, so let's try an example problem, the first one. And the problem says, what is the current drawn by a 100-watt light bulb operating at a potential difference of 120 volts? Because for us in Canada, that is where, that's how much voltage you get coming out of your outlets. Most outlets, anyways, is 120 volts. Okay? Now this is a 100-watt light bulb, so I'm assuming it's an incandescent light bulb, because a 100-watt LED light bulb would be extremely bright. But maybe there's some of those around. I don't know, actually. So power. We're given power right here. That's P. And we're given potential difference, which is voltage, V. And we're asked to solve for the current. What is the current, I? So in our equation, I equals P divided by V. So I equals P divided by V, which is 100 watts over 120 volts. Okay, when you do that, you get 0.83 amps if you want to just round off to a decimal. Like that. Next, we're going to talk about electrical safety. Because 0.83 amps doesn't sound like a lot, but it's enough to do a lot of damage to you. Maybe even kill you. Great. Alright, so safety. Actually, let me come back to power later. So in an electrical circuit, you can be severely injured. So your body sends electrical signals. You have natural electrical circuits in your body, right? And that's used to send signals to communicate throughout your body, to your muscles, your heart, and so on. If you had another current passing through you, that would disrupt those signals. Right? Your muscles would contract or jerk violently, and that much current can cause your tissues to burn. So, very, very dangerous. And to prevent that from happening, you need to be a little bit self-aware. A wire like this, you should never be using. That's an exposed wire. There's a reason we have that outer layer on a wire. It's an insulating layer. So that if you were to touch any normal wire, you're only touching the insulating layer. You're not actually touching the metal that you have a current running through. This, you could actually touch that metal. And if you do, that electricity will choose to go through you. This is also very bad. So we learned that all of our equipment in a house is connected in parallel. And the more things you attach in parallel, the lower the total resistance of your circuit is. And the lower the total resistance means the more current. The more current going through there can produce overheating, fires, and so on. So to prevent that, well, one, don't do this. And two, we can use fuses or circuit breakers. Now, a fuse is just a part that's hooked up in your circuit with a thin piece of metal that will melt. When it melts, it breaks the circuit. And it's made to melt at a certain current. So, for example, if you have 15 amps going through, it'll melt. And it breaks the circuit. Now with fuses, once it's melted, you can't use it again. You need to go get a new fuse and replace that melted fuse. However, circuit breakers work a little differently. Circuit breakers have two different metals attached to each other. And when they're heated, due to a certain amount of current going through, because there's two separate metals that expand at different rates, they'll actually force it to bend. I'm going to pause here and I'm going to actually show you this. Alright, so that's our circuit breakers. Moving on, we'll also have these. Now these are in our science lab, and you'll probably notice them in your house where areas where there would be a water source, like kitchen, washroom, right? They're called GFCIs, which stands for Ground Fault Circuit Interrupter. And you can think of it almost like a circuit breaker right at that outlet. So instead of the circuit breaker being in your basement, right, it's right there. So it can stop it immediately. And you would want something like that if you have water nearby, because that can be very, very dangerous. Another thing that can be dangerous is we've talked about how a short circuit can be dangerous. I mean, it makes sense. You don't want to attach a circuit with no load. And so no one would ever do that on purpose, but you could accidentally do it. You've seen how complicated our circuits can get. It's possible in a complicated circuit, you accidentally give the electricity a path it can take that doesn't go through any loads. And if you give it that path, it will take it, because that will be the path of least resistance. Your light will not turn on, and you've created a short circuit, which leads to possible fires. Another thing is in your car. Now, let's say something terrible happens and there's like a broken wire that's on your car. And that electricity needs somewhere to go. Now, what it's doing is it's trying to get to ground. And your car allows that electricity to go around it and shoots down from the sides. This is called a Faraday cage. Now, lots of people think that the electricity can't get to the ground because your tires are insulating. Right? That depends on how much electricity there is. It takes about 10,000 volts for electricity to be able to pass 1 centimeter of air. So let's say your car is 10 centimeters from the ground, if you're not including the tires. Well, that means if the electricity was 100,000 volts, yeah, it can easily bypass the tires and get to the ground. If your car got hit by lightning, well, there was enough voltage for the electricity to go from the sky down to your car. Your tires are not going to help you. It's got more than enough electricity to bypass your tires and jump to the ground. What helps you is that sort of cage structure of your car, which gives electricity an easy path to go around. And again, it'll take the easiest path. What you want to make sure you do in this situation is not get out of your car. Or if you do get out of your car, you're going to have to jump. Do not open your door and then grab onto the side to step out of your car. The instant you grab onto the side, you've given electricity an even easier path to get to the ground. And that will be through you. And that's where things can get extremely dangerous. Let's try our next problem. Now, it says one of the warnings printed on battery packs state, do not carry batteries loose in your pockets or purse. Let me explain why. Alright, here's why. So, you have two batteries. Okay, this is the rarely seen C battery. Although I used to see it all the time when I was a kid. Now, not so much. And a 9-volt battery. But you can imagine this being a AA, it doesn't matter. Now, if I just hold these loosely in my pockets, they might be moving around, and eventually they could come into contact like this. Well, what is that? This is the positive and negative side of the battery, and this is metal. If they come into contact like this, I create a short circuit. Right? Just like this. Short circuit created. And you're going to start to realize if these are in your pocket is getting extremely hot. Okay? So this is why you do not carry them loosely. Okay? If you are going to carry them, then you should, especially over 9-volt batteries, you should put some electrical tape covering the top. Or maybe keep them in a separate plastic container on its own. Not together in the same container, but in its own separate container. Alright, so getting back to this question, these can connect and form a short circuit, which is again what you don't want to do. So what you can do, even when you dispose of them, is put your insulating electrical tape over top of them before you put them into a disposal bag, which then you should bring to a proper recycling plant. And one more thing I wanted to go over, which I skipped, is our electrical power. So this is kind of interesting. So we have power plants that create a certain amount of power. Now we do not have a good way of storing power. Sure, we can store energy inside batteries, but it's not the most efficient, and we do not have enough batteries, or it doesn't become efficient to store enough power that an entire city would use in batteries. So batteries is not a solution to store electrical power made at power plants. Now there are lots of other ideas that people have come up with to try and store energy, such as using leftover energy to, say, lift something, which then can be dropped later and converted back into electrical energy. But again, nothing is very efficient or good enough to use on a big enough scale. So, we create power as it's needed. If the city is using a little bit of power, the powering plant only creates a little bit of power. As the city starts to use more and more power, they use more and more and more power. Eventually, you get to the limit to what a powering plant can put out. And if the city still is using more and more power, then you have a couple options. Option A, cut off power in certain regions. We call those brownouts instead of blackouts. Right? Option B, purchase power from a neighbor. Maybe from a neighboring city or even a neighboring country. Right? Canada and the U.S. are constantly purchasing power from each other. Now that becomes more expensive for a city if they have to purchase it from a neighbor, which is why they ended up creating our time of use. Right? So it becomes more expensive for us to use electricity during the day when it's at its highest use. Okay? So that's why we should probably try to follow that. Use power more often during in the low hours than the high peak hours, right? Because know that eventually your city will start purchasing it from neighbors.